Yeah, hi and welcome everyone. It's my first PyTorch conference. I'm excited to be here. And yeah, today I'm talking about the architectural timeline of LLMs. So this is going to be a 15-minute talk. It's a bit, of course, challenging to cram everything that happened in the last 6 years into, let's say, a 15-minute slot. But I was thinking to give you a brief overview of what has changed in the last 6 years since the release of GPT-1 and all the changes that brought us to Llama 3.1, which was just released a few weeks or let's say 2 months ago. So of course you may know a lot has changed in terms of model sizes. Back then, like a GPT-2 model was 124 million to 1.5 billion parameters. Model sizes got bigger over the years. The common sizes are between 7 and 70 billion now with Llama 2 and Llama 1. And then recently in Llama 3.1 we got this huge model, 405 billion. I would say though the sweet spot for me or most people is still like the 7-8 billion model. So, but just to give you an update on what has changed on the model side. Dataset wise, there's also been a lot of changes. Things get bigger. So you have GPT-2 with 40 billion tokens, Llama 1 with 1.4 trillion tokens, 2 trillion tokens for Llama 2, and then 15 trillion tokens for Llama 3. So things got a lot bigger. But I would say this is maybe the most boring update here. It gets more interesting when you look more into the recipes that the teams used for training the latest models. For example, now in 2024 compared to back then when the first GPT-1 model was released, what's becoming more popular and common is really spending a lot of time on the dataset filtering, like developing quality filters, even developing LLMs that check your data and remove low quality data. So that means basically not always more data is better. Of course, more data can be better, but the quality has to be good for that data. And then there's also an increased focus on dataset mixing. So with that, I mean like focusing on methods that develop an optimal dataset mix for the downstream, let's say, tasks you're interested in. That usually includes, for the pre-training, making sure the model sees, of course, high quality texts, but then also diversity of texts, general knowledge, let's say medical knowledge, math, code, and so forth. So there's also like a more like sophisticated paradigm now to develop this dataset mixing. Synthesizing additional pre-training data is also something that is, I would say, on the horizon. A lot of recent LLMs, they also use synthesized data, which means basically that you use another LLM to create data and also to reformat and to reprocess data. And then, interesting trend is even including Q&A data, which was traditionally just used for the instruction fine-tuning as part of the pre-training process. So there's a lot of changes in the recent, I would say, years that brought us to Llama 3.1. And one of the, I would say, biggest changes also in the recent models were these multi-stage training paradigms. Back then, GPT-1, GPT-2, it was just a single, relatively simple training loop. Nowadays, the pre-training consists of multiple stages. So first, just the regular pre-training, then there's usually a long context stage where you would focus on very long documents that are high quality, and then train the model with a longer context on these long documents, which helps essentially later on with processing longer inputs and information retrieval. But then there's also like a high quality annealing phase where you would particularly select those high quality data points with another method to feed them back into the LLM at the very end to anneal the LLMs to get a better performance. So just to, before I go to the more architectural changes, just to summarize, there has been a lot of changes in how LLMs are trained compared to GPT-1, the early days. So when I was reading the recent papers for Llama 3.1, Gwen 2, and Apple Foundation models, you can see that most of these techniques are currently used to train these base models. So most of those open weight models, they use a selection of the techniques I just mentioned. Apple Foundation models, I think it's not an open weight model, but at least they shared a lot of details in their research paper to also get a glimpse of how the recent models are developed. I must say there is one outlier though. So if you look at Gemma 2, based on the paper, you can see they didn't use most of these techniques. Yet I would say Gemma 2 is still one of the most, or it's among the most powerful pre-trained models in a convenient 2 billion to larger sizes. So it doesn't mean you have to use all these techniques. They made a few more architectural changes, which I will get back to later. But most of the nowadays pre-trained models have the more sophisticated pre-training recipe. Since since today, basically, there has been also a lot of changes in the fine-tuning. I'm not going over this because, yeah, it's just a 15-minute talk, but I'm happy to chat more also on the fine-tuning, which is something I specialize in. I wanted to, for the remainder of the talk a bit about the architectural changes, which is the main theme for this talk. So when we look at the original GPT architecture, it looks somewhat like this, and there are a lot of little blocks you can see there. And you don't have to really understand all the blocks. The interesting part will be just seeing what has just changed compared to Llama models. So there's a lot of stuff going on here, but essentially what's nice is that all these blocks are kind of reused in other LLMs. So just focusing on GPT-2, which is very similar to GPT-1, is exactly the same architecture, except it comes in different sizes. And then to just narrow it down, let's say we focus for now on the 1.5 billion model. And so this 1.5 billion model has transformer blocks in the center that are repeated 48 times. Then you have a certain number of attention heads, here 25. And then you have also the absolute positional embeddings with a size of 1,600. And so when you take the same 1.5 billion model, the GPT-2 XL model, and compare it to a Llama model, so here in this case the first Llama model, you will see there is actually not that much that has changed. It's relatively simple. The whole block in the center is basically the same. There are small changes, for example, in the vocabulary size. So here in Llama 1, the vocabulary size is slightly smaller because it used a different tokenizer. Then the layer norm got changed to RMS norm, which is essentially just another way of normalizing the activations. The dropout got removed, which makes it a bit simpler. And other than that, you can see it's mostly the same. At the bottom, you can see there's a small change from absolute positional embeddings to rope, where rope stands for rotational positional embeddings. It's a relative embedding method. But overall, the message here is these architectures are fundamentally very, very similar. And then if we take this Llama 1 model that I've just shown you on the previous slide and compare that to Llama 2, again, it's very similar in this, in this context here. It's actually almost identical except for the very bottom at the right, where the embedding size got changed from 2,000 to 4,000 tokens, so it can process longer inputs. Fast forwarding from Llama 2 to Llama 3, again, only a few changes. So again, the same base architecture. But there's a big change in the upper right in terms of the vocabulary size. So here, in this case, it increased from 32,000 tokens to 128,000 tokens, which means that the vocabulary has much more different tokens, which helps a lot with reducing also the context size for the input, because then you don't have to split the tokens into too many sub-tokens, essentially. And also it supports more languages and could be also more easily fine-tuned for coding tasks and so forth. There's also a change here in the center. It says grouped query attention instead of saying masked multi-head attention. So what is this grouped query attention? This is something that was already added in Llama 2 for the larger models, but it's also now here in this smaller Llama 3 model in the 8B version. So grouped query attention is essentially like a trick to make attention more efficient. So like a sharing of weights. So here on the left-hand side is the regular multi-head attention. Since this is only a 15-minute talk, I can't go into too much detail, but the key message here is in regular multi-head attention, you have, for each query, you have a key and a value pair. And in grouped query attention, two queries are sharing, for example, the key and value. So this is an example where you have a group size of 2, but you can also increase the group size to 4 or 8 and so forth, where you have multiple queries that share the same K and V, keys and values across multiple attention heads. It's essentially, the takeaway here is to make it more efficient, so to use fewer parameters, essentially. And one of the main takeaways of this talk is also to show you, okay, these different architectures, they are fundamentally relatively related. They are all derived from the original GPT model. And that allows us to implement these also in a combined code base. So I'm helping maintaining an open source library called LitGPT. And in this library, we have a model class. It's called GPT. And it is 500 lines of code. It's actually not that much, and it can support all these different models because the architecture is so similar. So, for example, you can plug in a Llama 3 model here just with certain settings in a config dictionary. But you can then also plug in a Microsoft Phi 3 model because honestly, it's not that much different. It's just some numbers that changed here, but you can really reuse most of the code for implementing all these different models. Or Mixtral. So Mixtral is an interesting one actually because it has this mixture of experts level, but it's also not that much, I would say, different from GPT. So what is mixture of experts? So mixture of experts is essentially swapping out this feed-forward part by multiple blocks, and in the sense it's also a trick to develop larger models but make them still relatively efficient during inference. So for example, if you have a 47 billion mixture of expert model, in this case only 2 of these experts of these blocks are active during inference, so you still have only 13 billion parameters active during inference. So yet another small modification but not fundamentally changing the transformer architecture. Or Gemma 2, I mentioned this earlier. So Gemma 2 has a few more, I would say, custom modifications, which makes this dictionary a little bit longer, so there are a few more settings, but fundamentally, it's also still relatively similar to GPT. One interesting thing that also recently got added to LLMs, so they were not the first one to add this. I think Falcon might have been one of the earlier ones. But what they did is they added something called sliding window attention. And if I just give you a brief introduction, so sliding window attention is yet another way to make things more efficient. On the left-hand side, that's our regular causal self-attention mask that is used in most LLMs, where for each given token, you attend this current token and all the previous tokens. And in this sliding window attention, you are restricting how many tokens you attend for a given token. So it's essentially limiting what a certain position can see as the context, yet as another way to make things more efficient, to save computation, because attention mechanisms, they scale quadratically. So with the token size, there are of course many different approximations, but if you look at the current LLM landscape, no one really uses these approximations for the pre-training of LLMs. It's usually just the sliding window attention that has gotten some traction here in this case for Gemma 2. So just also to summarize the recent or relative focus of these different areas for developing LLMs, there is of course the model size that got bigger over the years a little bit, but then I would say the sweet spot kind of calibrated to the 7 billion to 70 billion size. There's this exception of Llama 3.1 with a 405 billion size, but other than that, I think most of you might be still using 7B models, and that's because it's a really convenient size. So I think the recent progress in recent years, it was not necessary through the model size, but other things. So for example, there were some architecture improvements, like what I mentioned was the grouped query attention, the mixture of experts, and the sliding window attention. But really, I think a lot of time and effort and sophistication has been spent on improving the post-training recipes. So with that, I mean developing better methods for RLHF and DPO, and it's nowadays mostly a multi-stage process. So it's not just like a single pass anymore. It's more like going back and doing rejection sampling and so forth. And then, of course, still what's most expensive is the pre-training. And like I mentioned in the beginning, the data mix is really important, data quality, and also this multi-stage paradigm of long context and annealing to high-quality data. So in this sense, I would say if you think about where most of the effort is spent, it's maybe on the pre-training because it's the fundamental thing that creates the LLM, then the post-training, and then model size and architecture innovations. I think we are still using the same things we used before. If you're interested really in understanding LLMs, how they are working under the hood, I have a new book where I'm building an LLM from scratch, from the ground up. That might be a nice way if you want to dive into implementing your own LLMs. Then we have this LitGPT library, the open source library I mentioned before, where we plug in different LLMs. And I think it's also a great way to learn how LLMs work. And yeah, it's also a very user-friendly interface. And lastly, at Lightning AI, if you need also compute, like GPUs, at Lightning AI, we also have a platform where we train, fine-tune LLMs and other things. And with that, I think the 15 minutes are over. Thanks for attending. I know there was like a lot of context and a lot of information, but I hope I could give you a glimpse into how recent LLM architectures look like and how they compare to the early days. Yeah, thanks.